Hello, this is my SPED talk for senior project on machine learning embeddings, how we generate them, and why they're useful. So first off, what is an embedding? An embedding is a piece of data that's a low-dimensional continuous vector that represents the data. So here's an example. On the left we have this input data, which is an image, 64 by 64 by 3. So there's three integers representing, or rather 3 bytes representing the color of each pixel. And we'd like to get an embedding of this. So the first one, low dimensional, what does that mean? Well, this input data is about 12,000 dimensions. So that's 64 times 3. And we want to convert to a lower dimensional one, particularly 128. And so that just means that our embedding is a lot smaller. Now what does continuous mean? So in this case, think about this input data. All of these pixels can be, suppose they can all be a random value. And think about how many of those random orientations are valid pictures of, in this case, articles of clothing. The answer is very, very little. And so we say this is a very jagged or non-continuous input space. Embeddings are continuous. So this embedding here, it's only 128. You can randomly assign these values, and it will still be a valid representation of some image. Now lastly, the representation. This means that this embedding should somehow convey the meaning of this article of clothing. So why are they useful? Well, the key element is because the embeddings are continuous, it makes them a lot easier to train with. If you have any experience with neural networks, you know they train via something called gradient descent. They want a smooth error space that they can kind of roll down. But with a jagged error space, like in the case of a book or a sentence, the difference between one sentence and another, where there's only one word difference, one can be perfect fluent English and then one can be totally random gibberish. And so it has a really jagged error space that's difficult to train. Embeddings can take it and put it into a continuous representation that's a lot easier to, the error space is a lot smoother. So here's an example I have. So this was a classification task. There are 13 labels and we're trying to classify an image. There are two models used. The first one's a traditional convolutional neural network, and the second one is a super simple feed-forward network that takes in the embedding of the image. The convolutional neural network, even though they're the same, the convolutional network is just adding the embedding process in with it. It achieves much lower accuracy. The reason why is because it's just so much harder to train this. With this one, it's super simple because a lot of the solutions are valid. So now how do we create this? Well, there's no data set that maps your input data to your embedding. It just doesn't exist because these embeddings need to be meaningful to your specific data set. So we use clever techniques to try and determine the quality of our embedding network. And the one I want to talk about is image reconstruction. Now this is a technique that are called autoencoders. And the idea is we have an encoding network and a decoding network which are stitched together. So they're trained at the same time. And the encoding network is asked to create a lower dimensional embedding of your input image, and the decoding network is asked to reconstruct the image from the embedding. And the error of the model altogether is given as the error between the two images. And so after you're done training, you just throw away the decoder, and your encoder is now a useful image embedding network because this embedding is detailed enough that it could reconstruct the image from it. So how does this lead to my project? Well, my project is trying to create a network that can determine how fashionable a given outfit is for a given person. So just determining how fashionable an outfit is a relatively simple task. The difficult part is how can we customize it to the individual? Because in this case, we don't just need an embedding of the outfit, which is we can do with the autoencoders to create embeddings of the images. We need to create an embedding of the person's fashion sense, and this is a lot harder. So how does my project go about doing this? Well, the key is to create a network which modifies the user embedding, or more concretely stated, it takes in a user embedding and a user rating of a given outfit and produces a vector which, when applied to the original embedding, produces a more accurate embedding, where we define accurate as when applied to the prediction model is better at predicting whether or not the user will think it's good. So this example, we start with an empty embedding, and this is a super simplified one with only 2 dimensions, but in reality the embedding will be a lot higher dimensions. And it takes in a rating, and the embedding network produces a new vector to modify the embedding such that the prediction task is now more accurate. And you see in this case, it clusters around this one. So that means that the prediction network, given a user embedding in this area, is relatively accurate to what the person actually wants. So in summary, embeddings are super useful because they tend to be these continuous data representation, and that's what I'm using for our project.